So in our first lecture, we kind of talked about some ideas and some concepts and a little bit of background of what we're doing and why we think we're going to get a good answer and so forth. But let's get into a little bit of the nitty-gritty, some of the details on our problem that we were talking about, the analysis of a tapered bar. And so in this lecture, we're going to introduce a concept called the bar element, as well as some fairly useful concepts in general for finite element analysis. Some of the concepts that we're going to talk about for this one-dimensional type bar element can be applied in the larger sense to different two-dimensional and three-dimensional elements as well. Now, in order to have a little bit more room to work with, instead of having my bar pointing downward, I'm going to have my tapered bar kind of sideways here like this, and we already know that we want to break this up into various rods, and it's just kind of dependent on how many we want to break this up into. Now, for the purposes of our discussion, one really isn't enough, and any more than 4 is too many to really write down, and I think we'll be able to illustrate all the concepts that we want to if we take and we break this physical system, which is the tapered bar, into a representation of 4 different elements. Okay, so what I'm going to do is I'm going to break this up into, we can use equal lengths or we can use non-equal lengths, it doesn't really matter. Maybe if I spread this out just a little bit. I want 4 elements. Maybe I'll use a different color to emphasize this. So there to there, there to there, there to there, and there to there. So what I'm going to try to do, my convention that I'm going to try to do, is when I number elements, I'm going to number them and I'm going to put a circle around them. 1, 2, 3, 4. And what we've done is we've taken this physical system and we are representing it so that we can use a computer. We are discretizing the continuous structure. Discretization. That's an important step in applied finite element analysis. Now, these little dots that I've drawn here, those represent the ends of each of those 4 elements, and those are called nodes. And so to represent those, I'm going to go 1, 2, 3, 4, 5. I'm going to have 5 nodes. With 4 elements. Now in finite elements, we do talk a lot about a global numbering system and a local numbering system. Okay, so this is the overall structure. These would be in the global numbering system. Now the reason why we want to distinguish between the global and what I'm going to call the local numbering or coordinate system is that if we really look at this, there really isn't any mathematical difference between element number 1 and element number 4. Now sure, they may have different properties such as their areas and their lengths, but the algebra that we have to do, the basic formulation of those is the same for each one of those particular elements. So what I can do is I can pull out one of those little pieces, and we're going to look at that in a lot more detail. We're going to look at a single bar element. So let's see, I'm going to try to keep using red for the element color. So we have one element that I'm going to pull out here, and this is just your typical element. I'm not saying it's any one of those in particular, but it's just a general thing that I can have. And it's a particular element. This bar element can only take axial forces and can only deform in the axial direction. Now I know my real structure can deform in the transverse direction as well because of Poisson's ratio and all those good things. But for our analysis, we're just interested in the extension of this structure. So we're only interested in things that happen in the axial direction. So on this local element system, and I'm going to go ahead and use blue at the risk of being confusing. But the number 1 and number 2 could be number 1 and number 2 over in the global numbering system, but it could also be node number 4 and number 5. There's going to be a mapping from the nodes in the local system to the global system. Alright, so the lower numbered node is on the left, the higher numbered node is on the right, and that's perfectly fine that we can do it that way. Associated with each of those nodes would be some force. And so our coordinate system is going to go this way. And probably what I need to do is I should put that at the left node, just to be extra clear. Positive axial direction is that way. And I can talk about a force that's in node 1 and a force that's acting on node 2 from that element. Now, if this is an equilibrium, their magnitudes are going to have to be equal, and we'll get into that in just a little bit. But let's just say we have a force at node 1 and we have a force at node 2, and we're going to draw them in their positive directions according to that coordinate system. Each of these nodes also have some displacement. Okay, now the displacement is the movement of a node or a point on that structure. It's a little bit different than the x that we used for the spring, which was the extension. That was the change in length of the spring. Here we're talking about the displacement. Now extension is important, and we will see how to calculate that from the displacements. Alright, so we'll get back to this picture in a little bit, but let's focus on our local little bar element right here. So we have this bar element, and we got the force F1 over here, and we have the force F2 over here. If I want to keep this in equilibrium, we'd have the summation of forces down the axis equal to 0. I'd have a plus F1 and a plus F2 equal to 0. And so, really the force F2 in this particular case is equal and opposite. It's the negative of the force F1. We just talked about displacements and extension. So let's also make a little note here. If U1 is equal to U2, not necessarily 0, it could be 0, but even if it's a non-zero value for the displacement, if the displacement of node 1 and the displacement of node 2 are 0, then there is only a rigid motion. So that little segment doesn't extend, and because, just like springs, if the spring doesn't stretch out, we don't develop a force in it. There's no force inside of that bar. Now, in the previous lecture, we talked about how we could compute the change in length of a bar being equal to FL over AE, and we wrote it this way: F is equal to AE over L, and then times the delta L, and we call this the stiffness K. And for our bar or rod element, we can call this the stiffness of the bar, the AE over L. And those are numbers that we can compute when we're ready to. But right now we'll just leave them as that symbol. F is equal to K times delta L. Now, if this were to stretch out, then that means that the displacements U1 and U2 are unequal. And then we can say that the force at position 1 would be equal to AE over L times the difference in those two displacements. And since the force F2 is equal to the negative of the force F1, we can write it this way, that the force F2 is equal to AE over L. Well, let's do it this way. I can say it's U2 minus U1. So we can say that it's K, U1 minus U2, and here it's K, U2 minus U1. Let's take a look at those equations. Let's make a little bit of room. Alright, so this kind of begs for us to write this in a matrix format. So, you know, matrices can represent systems of equations. So let's do it this way. Let's put the forces over on the left-hand side, F1 and F2. We'll write the equations out, then we'll write the matrices. But in terms of the spring stiffness K, or the rod stiffness K, we're going to have a K U1 minus a K U2, and here we're going to have, I'm going to write it this way, a minus K U1 and then a plus K U2. And so in the matrix format, we'd have a vector over here on the left-hand side, and a matrix. I could put K out in front, but I want to emphasize some things about this matrix. So I'm going to leave these K's in here, and then I have the displacements for the local nodes 1 and 2 as a vector. Alright, so this term right here is called the element stiffness matrix. This is the force vector. And this is the displacement vector. And so if I knew a couple, one of these forces maybe and one of the displacements, then I'd have two equations and two unknowns. Assuming I knew my cross-sectional area and my material properties and the length of that little segment, then I can solve this matrix and I can figure out what my two unknowns were. Okay, so this is going to be an important concept. Like I said, computers really like basic arithmetic operations, addition, subtraction, multiplication, division. So anytime that we can write this in a way that enhances the ability to see this as a basic arithmetic problem, then the better off our computer is going to be. Okay, so this is kind of an interesting idea then. Let's go back to our original picture where we had the 4 elements, and we're going to try to see what goes on in that case. Now I think at this point it would get too confusing if I had to do a mapping between a local coordinate system and the global numbering system the global coordinate system that I have. So what I'm going to do is I'm going to use the global numbering system, and I'm going to write some equations out in the global system. The way that the finite element code will work is that it will do this mapping automatically, and computers are really good at re-indexing things and referencing things and so forth. So all of this happens very quickly and very easily inside the computer. Human minds don't tend to work that way, so we're going to try to do this in a way that seems more reasonable from our perspectives. So we have these 4 global elements, and we have these 5 nodes. And so for each of these, I'm going to draw them out separate from one another. And I'm going to stagger these so that we can kind of see it this way. So there's 1, there's 2, there's 3, and there's 4. And each of these have maybe different properties. So we said previously that maybe we'd use the large diameter as the diameter for the entire segment that we have here. So in other words, it's going to have its own stiffness. I'm going to call that K1, K2, K3, and K4. And so we have our nodes 1, 2. Now, element 1 only has the node 1 by itself. Node 2 is shared by 2 different elements. So there's 1 and 2 and then 2 and 3 and then so forth. And then finally we get to the end, and then 5 is kind of by itself too. And associated with each of these are displacements. So there's one, this one I'm going to kind of put in between the two, kind of emphasize the displacement of those like that. And we can generate a big system of equations just like we did previously for each of the nodes in the single element that we talked about. Okay, so what do I mean? We had an equation last time on the previous page for the local element. It was F1, and it was, what do we have? Let me make sure that I'm saying it right. We had K times U1 minus K times U2. And that's what we're going to have here, except instead of using the generic K, I'm going to use the specific K sub 1. So F1 would be equal to K1 U1 minus K2 U2. And now we go to force 2. Now force 2 is a shared node between 2 elements. There's an element 1 and there's an element 2. Now force 2, if it were all by itself, we saw that it was equal and opposite to what we have for force 1. So it would be a minus K1 U1 plus a K2 U2. But it's also influenced by the stiffness and the displacement due to element number 2. Oh, sorry. I'm getting carried away here. I have to be very careful. These are both for element 1. But force number 2 is also influenced by element number 2. So that is when the stiffness of element 2 will be incorporated. Now, element 2 has its node number 2 on the left-hand side, so it's going to look like this. It's going to be a plus K2 times the left node displacement minus K2. See if I can get over here without that turn on. Minus K2 times the right node displacement. All right. Let's do number 3. Force 3 is going to be influenced by elements 2 and element 3. The left side is going to look like this, minus K2 U2. It's the equal and opposite of this, plus K2 U3. Alright, and now there's going to be a K3 stiffness, K3 U3 minus a K3 U4. Node number 4, the force, is going to be influenced from a stiffness from element 3 and element 4. It's going to look like the equal and opposite of this term that I just wrote down. It's a minus K3U3 plus a K3U4. And then it's going to be influenced by the stiffness of the right side plus K4U4 minus K4U5. The force on number 5, okay, that's sitting all the way out there, and there's nothing to the right of number 5, so it's only influenced by what goes on inside element 4. It's going to look like a K4U5 minus a K4U4. Alright, so we built this out of a superposition of what goes on in our single element, noting that we can add the forces together from the effects of 2 elements to see what goes on at that particular node. So if we look at this, it's kind of interesting. It's got a lot of these stiffnesses in it. It's got 1s and 2s and all these displacements. We can also write this in a matrix form as well. And let's clean off a page and let's do that. Alright, so I shrunk those down just a little bit. But let's write our matrix over here. We're going to have a force vector that's going to have 5 terms in it. We're going to have a big matrix. It's going to be 5 by 5. I think that'll be enough room. In fact, maybe it won't be. So let's give ourselves plenty of room to work. I don't want to get too crazy with it. And then over here is going to be my displacement terms. Displacements of each of those nodes. 1, 2, 3, 4, and 5. Alright, so let's build our matrix based on what we have over here. Our first line is we have a K1 U1 and we have a minus K1 U2. Our second line has U1 U2 and U3 in it. Alright, so U2, so it has a U1 in it, so that's a minus K1. And U2, notice that there's 2 terms. I'll try to circle these. There's a K1 U2 and a K2 U2. So I'm going to add those together to get this entry right here. It's a K1 plus K2. And then we have a minus K2. times U3. Alright, so I'm trying to keep my columns a little bit separate. Now I have my F3. F3's got a U2, U3, and a U4 term in it. Okay, so it's a minus K2, and here there's a K2 and a K3. And then I'm going to have a minus K4. Number 4, F4, has a U3, a U4, and a U5. So U3 has a minus K3. It's got K3 plus K4. And then it's got a minus K4. Then we get to the end. For F5, it's only got a 4 and a 5. It's got a minus K4, and we have a plus K4 in this position. It's not added anything because it's on the end. All the rest of these things are 0, okay, because there's no U5 term in the F1 equation. So I'm not going to write it down. This is called a global stiffness matrix for the structure. If we know that one of the displacements is 0, and we know all the values, we can calculate K, and we can go back and know some of these forces. We can calculate the knowns and the unknowns. But just by itself, this global stiffness matrix is very interesting. One of the things that you'll notice about this, first of all, is that it is symmetric. Okay, we got different terms along the diagonal, but the corresponding off-diagonal terms, the symmetric terms, are symmetric. And this is what will happen when you assemble global stiffness matrices. If you end up with a non-symmetric global stiffness matrix, it usually means that there's something weird about your analysis, or kind of non-standard. But a linear elastic finite element analysis is going to have a symmetric stiffness matrix. Now, if you're a computer, that's really good for you because you don't have to use your memory to store the other side of the diagonal terms. You know that it's symmetric, so those terms, like above the diagonal, do double duty. We know that it's symmetric, so there are certain ways that we can use in computers to take advantage of knowing that we're solving a symmetric matrix. Suppose we want displacements and we know all the forces, then we can invert this and we can solve for those displacements. We can come up with a global compliance matrix, if you want, instead of a global stiffness matrix, by finding the inverse. The other thing that I can point out about this matrix is if we look at this, it's really kind of interesting in the fact that if we looked at our single element stiffness matrix, and I'll do this in red, remember our single element stiffness matrix looked like this. Now there's no subscripts on here because it's just a single element stiffness matrix. So it's not an element 1, 2, 3, or 4. It's whatever element we want it to be. But if we look at this, that actually occurs in these terms right here. And then the next two lines below the first one, the second and third line, well, we're kind of adding the element stiffness matrix, and we're sticking it into the big global stiffness matrix. Okay, so here's K2, K2 minus K2 minus K2, and then of course there's a plus K3 and a minus K3. I think I must have messed up somewhere here, because that should have been a minus K3, and in fact it is. Still not blue. And then this one down here. So if we were trying to make the most efficient use of our time as possible, I really didn't have to write all these equations out. If I know I have a series of bar elements that are connected like this, I can just overlap my element stiffness matrices in my global stiffness matrix. Some people call this assembly, stiffness matrix assembly. Another thing that we can notice about this particular matrix then, besides this overlapping nature, is the banded nature of this. See how all the terms that I've written out here are along the diagonal? Now, if I had ordered my nodes in kind of a weird way, just random, 5, 3, 2, 4, 1, then I'd have still a sparsely populated matrix, but it wouldn't be banded if I did it this way. Well, it turns out dealing with banded matrices is also a very efficient thing. Sparsely populated matrices are a lot more of a headache to deal with. Like I said, we're trying to minimize our computations. And so the global node and element ordering are kind of important. Now, fortunately, in modern finite element programs, whatever you decide to order your nodes or call your nodes, behind the scenes, your finite element code is renumbering those for you so that it can have a sparsely populated banded matrix that is symmetric. And so it can work with that easier. So that's something else that you might want to know if you end up taking a class where you code your own finite element program. Global stiffness matrix assembly is much easier when we have a nice, some people call it a wavefront, an ordering of these nodes. All right, so let's just write down a few of these things, and then we'll call it done for this lecture. All right, so again, just some things to notice. There's a lot of zeros in there. It's a sparse matrix. The matrix is banded due to the numbering scheme that we used. The matrix can be assembled from the superposition of local element stiffness matrices, and what we did, if we think of it that way, is we have formed a global, or assembled a global stiffness matrix. Okay, so as we go out through the semester, I want you to be familiar with some of these terms that you might read in the user's manual of your finite element code or the theory manual. And so we'll try to use some of these terms. Some you may be familiar with, some you may not, but we'll try to put these in context, and we'll try to make things simple enough, but understanding that these can be extended to much more sophisticated things. Instead of one-dimensional route elements, we can do something very similar for three-dimensional, 20-noded cubic elements, whatever we have. All right, so this is good for that one.